NEC Article 310.15b16 addresses the protection of cables installed in raceways that are exposed to high short-circuit currents. This article stipulates that these cables must be protected against damage stemming from the magnetic forces that are produced by these short-circuit currents. Short-circuit currents can generate substantial magnetic fields. These magnetic fields induce mechanical stresses within the conductors and the surrounding raceway. If not properly addressed, these forces can lead to several undesirable outcomes. Firstly, insulation failure. The intense magnetic forces can cause the conductors to move violently within the raceway. This movement can abrade or otherwise damage the insulation surrounding the conductors. Compromised insulation increases the risk of electrical breakdown, arcing faults, and ultimately, fire hazards. Secondly, conductor deformation. High short-circuit currents can generate significant heat within the conductors. This heat, combined with the mechanical stress from the magnetic forces, can cause the conductors to deform or even melt. Deformed conductors reduce the current carrying capacity of the circuit and increase the likelihood of future failures. Thirdly, raceway damage. The magnetic forces can also exert stress on the raceway itself. This stress can cause the raceway to bend, crack, or even break, compromising its ability to protect the conductors and potentially exposing personnel to electrical hazards. To mitigate these risks, several protective measures can be implemented. Firstly, proper conductor sizing. Selecting conductors with adequate ampacity for the intended application is crucial. Larger conductors have a greater ability to withstand the thermal and mechanical stresses associated with short-circuit currents. NEC Table 310.16 and other relevant tables provide guidance on appropriate conductor sizing based on ampacity and other factors. Secondly, secure conductor support. Properly securing the conductors within the raceway minimizes movement and reduces the risk of insulation damage. This can be achieved through the use of cable ties, straps, or other appropriate support mechanisms. The spacing between support should comply with NEC requirements to ensure adequate support. Thirdly, short-circuit protective devices. Overcurrent protective devices, such as fuses and circuit breakers, are essential for interrupting short-circuit currents quickly and effectively. These devices should be sized and selected to provide adequate protection for the conductors and equipment in the circuit. The interrupting rating of the protective device must be sufficient to handle the available short-circuit current at the point of installation. Fourthly, raceway selection and installation. The type of raceway used can also impact the level of protection provided against short-circuit currents. Metallic raceways, such as steel conduit, offer better mechanical protection and can help to contain the magnetic forces generated by short-circuit currents. The raceway should be properly installed and grounded to ensure effective fault current path. Fifthly, bonding and grounding. Effective bonding and grounding practices are critical for minimizing voltage differences and providing a low impedance path for fault currents. This helps to ensure that overcurrent protective devices operate quickly and effectively to clear short-circuit faults. All metallic components of the electrical system, including raceways, enclosures, and equipment, should be properly bonded and grounded in accordance with NEC requirements. Understanding available fault current. Before selecting protective devices, it is essential to determine the available fault current at the point of installation. This information is necessary to ensure that the protective devices have an adequate interrupting rating. Short-circuit studies can be performed to calculate the available fault current based on the characteristics of the electrical system. Another aspect to consider is conductor spacing. Minimizing the spacing between conductors in a raceway can reduce the magnitude of the magnetic forces generated by short-circuit currents. This can be achieved by using multi-conductor cables or by carefully arranging single conductors within the raceway. The NEC provides guidance on conductor spacing requirements in various sections. Furthermore, utilizing magnetic shielding. In some cases, it may be necessary to employ magnetic shielding techniques to reduce the impact of magnetic forces on sensitive equipment or components. This can involve the use of specialized shielding materials or designs to redirect or absorb the magnetic fields. Also consider the effects of temperature. High short-circuit currents can cause a rapid increase in temperature within the conductors and raceway. The temperature rating of the conductors, insulation, and raceway must be sufficient to withstand these elevated temperatures without degradation or failure. NEC tables provide information on the temperature ratings of various types of conductors and insulation. Periodic inspections and maintenance are crucial for ensuring the continued effectiveness of short-circuit protection measures. Electrical systems should be inspected regularly to identify any signs of damage, deterioration, or improper installation. Overcurrent protective devices should be tested periodically to verify their proper operation. Any deficiencies identified during inspections should be promptly corrected. The selection and installation of short-circuit protection measures should be performed by qualified electrical personnel who have a thorough understanding of the NEC requirements and best practices. Improperly installed or maintained electrical systems can pose significant safety hazards. It is important to note that NEC Article 310.15b16 is just one component of a comprehensive approach to electrical safety. Other NEC articles and industry standards also address various aspects of short-circuit protection and electrical safety. A thorough understanding of all applicable requirements is essential for ensuring the safety and reliability of electrical systems. The NEC, or National Electrical Code, is a comprehensive set of standards that govern the safe installation of electrical wiring and equipment in the United States. It is developed and updated by the National Fire Protection Association, or NFPA, and is widely adopted by state and local jurisdictions. The NEC is not law itself, but it is often adopted into law by reference. Therefore, compliance with the NEC is often legally required. The NEC covers a wide range of topics related to electrical safety, including wiring methods, overcurrent protection, grounding, and equipment installation. It is updated every 3 years to reflect advancements in technology and changes in industry practices. Electrical contractors, engineers, and inspectors rely on the NEC to ensure that electrical installations are safe and compliant with applicable regulations. Failure to comply with the NEC can result in fines, penalties, and even legal liability. Furthermore, it can create unsafe conditions that can lead to electrical shock, fire, and other hazards. The NEC is organized into chapters, articles, and sections. Each chapter covers a broad topic, such as wiring methods or equipment. Articles delve into specific aspects of the topic, such as conductor sizing or overcurrent protection. Sections provide detailed requirements for specific situations or applications. The NEC uses a numbering system to identify each section. For example, NEC Article 310.15b16 refers to a specific section within Article 310.15, which deals with allowable ampacities of conductors. The NEC also includes tables and figures that provide additional information and guidance. These tables and figures are often used to determine conductor sizes, conduit fill, and other important parameters. The NEC is a complex document that requires careful study and interpretation. Electrical professionals typically undergo extensive training to become proficient in the NEC. They also stay up to date on the latest revisions to ensure that their work complies with the most current requirements. The NEC is not intended to be a substitute for sound engineering judgment. It provides a framework for safe electrical installations, but it is up to the electrical professional to apply the code appropriately to the specific circumstances of each project. In addition to the NEC, there are other industry standards and best practices that can enhance electrical safety. These standards may address topics such as arc flash protection, surge protection, and power quality. Electrical professionals should be familiar with these standards and incorporate them into their work as appropriate. The goal of the NEC and other electrical safety standards is to protect people and property from electrical hazards. By following these standards and using sound engineering judgment, electrical professionals can help to ensure that electrical systems are safe, reliable, and compliant with applicable regulations. In addition to the specific requirements of Article 310.15b16, it is important to consider the general principles of overcurrent protection. Overcurrent protection is designed to protect electrical circuits and equipment from damage caused by excessive current flow. Overcurrent can result from a variety of causes, including short circuits, ground faults, and overloads. Overcurrent protective devices, such as fuses and circuit breakers, are designed to interrupt the flow of current when it exceeds a predetermined level. These devices protect the conductors and equipment in the circuit from overheating and potential damage. Fuses are one type of overcurrent protective device. They consist of a metal strip or wire that melts when excessive current flows through it. When the fuse melts, it opens the circuit and interrupts the flow of current. Fuses are typically used in applications where a fast response time is required, such as protecting sensitive electronic equipment. Circuit breakers are another type of overcurrent protective device. They use a mechanical mechanism to interrupt the flow of current when it exceeds a predetermined level. Circuit breakers can be reset after they have tripped, making them suitable for applications where overcurrent events may occur frequently. Circuit breakers are available in a variety of types, including thermal, magnetic, electronic, and solid state. The selection of an appropriate overcurrent protective device depends on a number of factors, including the voltage, current, and interrupting rating requirements of the circuit. The overcurrent protective device must be able to interrupt the maximum available fault current at the point of installation. It must also be sized appropriately to protect the conductors and equipment in the circuit. The NEC provides detailed requirements for the selection and installation of overcurrent protective devices. These requirements are designed to ensure that the devices provide adequate protection and operate safely and reliably. In addition to overcurrent protection, grounding is another important aspect of electrical safety. Grounding is the process of connecting the electrical system to the earth. Grounding provides a low impedance path for fault currents, which helps to ensure that overcurrent protective devices operate quickly and effectively. Grounding also helps to minimize voltage differences between different parts of the electrical system, which reduces the risk of electrical shock. The NEC provides detailed requirements for grounding electrical systems. These requirements cover topics such as grounding electrode systems, grounding conductors, and equipment grounding. Proper grounding is essential for ensuring the safety and reliability of electrical systems. In addition to the technical aspects of electrical safety, it is also important to consider the human factors. Electrical work can be hazardous, and it is important to take precautions to protect workers from electrical shock and other injuries. Workers should be properly trained in electrical safety procedures and should always use appropriate personal protective equipment such as gloves, safety glasses, and insulated tools. Lockout/tagout procedures should be used to energize electrical equipment before it is worked on. These procedures help to prevent accidental energization of equipment, which can cause serious injury or death. Electrical safety is a shared responsibility. Electrical contractors, engineers, inspectors, and workers all have a role to play in ensuring that electrical systems are safe and compliant with applicable regulations. By working together and following established safety procedures, we can help to protect people and property from electrical hazards. Furthermore, ongoing education and training are essential for staying up to date on the latest electrical safety standards and best practices. The electrical industry is constantly evolving, and new technologies and techniques are being developed all the time. Electrical professionals should make a commitment to lifelong learning to ensure that they have the knowledge and skills necessary to perform their work safely and effectively. NEC Article 310.15b16 plays a critical role in safeguarding electrical installations from the damaging effects of short-circuit currents. By understanding and adhering to this article, along with employing sound electrical practices and continuous professional development, we can significantly minimize electrical hazards and ensure the safety and reliability of electrical systems. The magnetic forces created during a short circuit are proportional to the square of the current. This means that even a relatively small increase in short circuit current can result in a significant increase in the magnetic forces. These forces can cause conductors to whip violently within the raceway, potentially damaging the insulation and leading to further faults. In addition to the mechanical stresses, short circuit currents also generate significant heat. The amount of heat generated is proportional to the square of the current and the resistance of the conductor. This heat can cause the conductor to overheat and potentially melt, especially if the conductor is not properly sized for the available short-circuit current. The combination of mechanical stress and thermal stress can be particularly damaging to electrical installations. It is therefore essential to take both factors into account when designing and installing electrical systems. The NEC provides guidance on how to calculate the available short-circuit current at various points in an electrical system. This calculation takes into account the impedance of the power source, the transformers, the conductors, and other components in the system. The calculated short-circuit current is then used to select overcurrent protective devices with an adequate interrupting rating. The interrupting rating of an overcurrent protective device is the maximum short-circuit current that the device can safely interrupt without failing. It is important to select devices with an interrupting rating that is greater than the available short-circuit current at the point of installation. Using devices with an inadequate interrupting rating can result in the device failing to clear the fault, which can lead to catastrophic damage and potential injury. In addition to the interrupting rating, it is also important to consider the clearing time of an overcurrent protective device. The clearing time is the amount of time it takes for the device to interrupt the fault current. Faster clearing times reduce the amount of energy that is released into the system, which minimizes the potential for damage. The NEC requires that overcurrent protective devices be selected and coordinated to provide adequate protection for the electrical system. Coordination means that the devices are selected so that the device closest to the fault will trip first, minimizing the impact on the rest of the system. Proper coordination requires careful analysis of the electrical system and selection of appropriate overcurrent protective devices. The installation of electrical systems should be performed by qualified electrical personnel who have a thorough understanding of the NEC requirements and best practices. Improperly installed or maintained electrical systems can pose significant safety hazards. It is important to ensure that all electrical work is performed in accordance with applicable codes and standards. Regular inspections and maintenance are also essential for ensuring the continued safety and reliability of electrical systems. Electrical systems should be inspected periodically to identify any signs of damage, deterioration, or improper installation. Overcurrent protective devices should be tested regularly to verify their proper operation. Any deficiencies identified during inspection should be promptly corrected. By following these guidelines, we can help to ensure that electrical systems are safe, reliable, and compliant with applicable regulations. In addition to the NEC, there are other industry standards and best practices that can enhance electrical safety. These standards may address topics such as arc flash protection, surge protection, and power quality. The electrical professionals should be familiar with these standards and incorporate them into their work as appropriate. The goal of all electrical safety standards is to protect people and property from electrical hazards. By working together and following established safety procedures, we can help to create a safer environment for everyone.